So we're getting into a lot with this. One is, how can you determine your latitude on Earth when you're outside? How do you know? If you even have a map, you don't know where you are in the map. And there are some ways to do this. The latitude one particularly stands out. So we're going to talk about the North Star. The North Star, the real name of the North Star is Polaris. Okay. Now, with some misconceptions that people often say, it's the brightest star in the sky. That's not true. It's not the brightest star in the sky. If you go outside at night and you can see the stars, the brightest star that you see is probably a planet in our solar system. They look like stars, but so it's not that. I'm going to show you how to find Polaris in a nighttime sky. But once you do, the Earth's axis points directly at Polaris, which, if I had a globe here, the axis points right out into space, and Polaris happens to be there. Crazy coincidence. And you can know the latitude as long as you're north of the equator, which is where we live, northern hemisphere, north of the equator. The angle between the horizon and Polaris, how high up in the sky it is, if you were to measure it, that equals your latitude degrees north. So here's just, I'm going to do some more here. I hope to throw in a video here, if I can edit it in, that kind of shows it. So I took this picture, this was in Long Island, New York, of the nighttime sky. It's hard to get pictures of stars, but this came out okay. So the first thing you want to do is find the Big Dipper. If you want to find Polaris, you need to find the Big Dipper. The Big Dipper, it looks like a pot or a ladle. I guess it's like you used to dip like a ladle in water in the olden days and drink out of it, like if you're a cowboy or something. I guess that's the idea of what a dipper is. So where is it here? It's kind of hard to see, but so I'm going to point it out. This is the Big Dipper, okay? I did the stars of the Big Dipper. I went over them in red dots, and now I'm going to connect them here. So this is the Big Dipper. It looks like a pot if I connected that across there, which I purposely didn't do, but that's the Big Dipper. Now, how do I find Polaris, the North Star, from there? These two stars here are your pointer stars. They're going to point out to space like that. They point out, and they will point to Polaris. Now, actually, in this case, Polaris is off my picture, so we can't find it. Let's use another picture from a friend of mine. Mike took this picture from his yard, and he sent it to me. What do we got here? Yeah, so not sure how well this comes through on the video, but you always want to find Polaris. And once you start finding it, it usually stands out pretty well in the sky. You can't see a lot of the smaller, more faint stars, or the more faint stars. You can't see them here, but you can see the stars of the Big Dipper. I outlined them here in green. How well do you see that? You see that? Okay. Outline them in green. And then these are the pointer stars, and we actually usually say, whatever this is, about 6 times the distance, about 6, so it's not super close, but out here, that right there, did I circle it? That is Polaris right there. So that's the North Star. So therefore, I know in northern situation, you find it, you go, oh, so north is that way. When you look up in the sky, you find Polaris wherever it may be. Maybe it's over there. Okay, that way's north if Polaris is there. So it helps orient you. So once you do that, the measurement you want to do is how high up in the sky it is. So we'll get to that in a second. Some other interesting things about Polaris. This is a state flag. Any idea what state of the United States this might be? I'll just take a random guess. Look at the landscape here, right? I mean, it's probably not New Jersey, right? But that is a state flag, and that is the state flag of Alaska. Okay, not a lot of people are that familiar with state flags. That is the state flag of Alaska, and because Alaska is so far north, it's the northernmost state, they sort of have embraced the North Star component. So they have Big Dipper on their flag, and they have Polaris, cool state flag. I like it in its simplicity. It has Polaris on it. It's pretty cool. This is a state flag of New York. Maybe not as cool. It's personal taste. Maybe you love it. There's a lot going on here. But it is personal taste. But just to give you an example, state flag of New York, Excelsior, our state motto, ever upward. Actually, I saw this yesterday, and I mean yesterday. This came up. I like the Alaska Polaris thing, so check this out. I saw this. This is the I guess it's Taku Lake Skate Park in Alaska. They just finished building this. They got this cool drone shot. I'm like, oh man, that looks sick. Look at this flow ball, that's killer. And I was like, what's up with the stars? And because I saw a picture of it earlier, I just saw one random star, but I realized this is in Alaska. Look at what they did here, because it's the state flag. They put a version of Polaris in there and the North Star in the middle of that ball. That's cool in my book. So you have this in your notes, and this, you know, they do this. You look at a nighttime sky, it doesn't look like this. Lines aren't drawn, they're not labeled like this. There's a million other stars out there. So it's not as easy as this, but it's just like sort of teaching you how to do it. So here's the Big Dipper, and then it points out in the sky. It's not perfectly, it's off a little bit. And Polaris happens to be the last star in the handle of the Little Dipper. Sometimes have kids go, why don't you just find a Little Dipper and it's the last star on the handle of it? The Little Dipper's hard to find. It doesn't stand out that much. The stars aren't that noticeable, while the Big Dipper is much more noticeable. Another version of it here, you have this as well. I really drew in the pointer stars. It also shows that different times of the year, different times of the night, the Big Dipper sort of changes, but it's always, those stars always point to Polaris. Polaris is the one star in nighttime sky that doesn't really change where it is because of the way that the axis of Earth points towards it, which gets complicated to think about. But another picture showing the same thing. You don't have this in your notes, but hopefully it goes. It's not really about being in your notes as much as it is about being in here, in your head. Okay, so how are we going to use Polaris, the North Star, to know what latitude we're standing at, like this? So Fred is here. The horizon is sort of off in the distance, is where, like I say, where the land meets the sky. So where the land meets the sky, if you can measure this angle, measure angle like in math. So in this case, it's 52 degrees above the horizon, if you can measure it. Therefore, his latitude, he's standing at, is 52 degrees north. You see that relationship there? Now, this is a different scenario of this area where these three houses are. Okay, if they measure this angle between the horizon and Polaris, it's 30 degrees above the horizon. Therefore, the latitude of these three houses is 30 degrees north. And you have to have north on there because it could be 30 degrees south. Or some kids could write 30 degrees west or 30 degrees east, but it's 30 degrees north. Make sure the north is on there. Okay, now we get into time zones, which is applicable to our life. So understanding this is going to start out with a picture that I took at a 6 a.m. sunrise on August 25th, 2015. I took this photo, sun rising over here. Okay, now the sun, with the sun rising, is coming right above the horizon. Now the thing, and if I time lapsed it, it looks, you watch the sun, oh, the sun rises, the sun's going up. The sun isn't really rising, the sun kind of stays there. Earth is spinning, it's rotating on its axis, and it makes it look like the sun is actually rising. So it's not the sun the sun isn't moving, it is in one spot, but because we're on Earth that's rotating, it causes the sun to rise in the sky for us. So if we look at this diagram here, the sun is over there. Now we're looking down at the North Pole, so Earth is rotating like this. This is a weird way to look at Earth. Earth is rotating this way. So in this case, I would be right here. And I often call sunrise is sort of when sunrise occurs, and I would look off that way to see the sun, and that's what we just saw in the previous picture, right? I'm looking off that way, I see the sun barely coming above the horizon. It's not up high in the sky yet, right? So sunrise is really, what do I often say? I say we're rotating out of the dark part of Earth into the light part. So the dark part is facing away from the sun, and the light part is facing toward the sun. So we're rotating right there. Now, if at that same time, at this moment when I took this picture, if I called my brother-in-law Brian in California and said, hey, check out this really cool sunrise going on, he'd be over here, because California is over 2,000 miles, it's 2,600 miles away. He'd be over here. It's 3 a.m. for him. He's only going to experience the sunrise 3 hours later. So this is why we have time zones. So it's still nighttime for him. He's not going to experience sunrise until his area of Earth, California, has rotated to there. Interesting to think about. And then at that same time, when I'm experiencing the sunrise, if I go on the other side of the Earth, China or maybe Australia, right? They're over here. Earth's rotating this way. They, on that same moment, they're experiencing sunset. Same time, I call them on the phone. I say, look at this great sunrise. We're talking about a sun setting. And that is why we have to have these time zones. So, and we're going to into that a little bit. So please copy this down. And each time zone is 15 degrees longitude wide. And I'm going to show why that is in a second. So, the United States here. So, if I'm experiencing sunrise here, as you go this, I'm going back in time. So, it's 6 a.m. here in California, where my brother-in-law is. It's 3 a.m. I don't know if you notice with sports games when I followed the East Coast teams, New York Knicks when I was a kid, the Mets, the Nets, teams like that. When they play on the West Coast, right, they start after work. Their games may start 7:30 California time when the Mets are playing, the Oakland A's or something. Although they just moved out of Oakland. When they're playing the LA Dodgers, let's say, it starts at 7:30 their time. It's 10:30 our time. It's really hard to watch the end of that game. I got to get my beauty sleep. I can't be staying up all those crazy hours. Another example. So this is in an airport. Airports will often have multiple clocks showing different time zones. Let's zoom in. So what this is showing, Eastern, that's where we live. New York, East Coast. It's 11 a.m. 11:10, and then you go Central. You're going across the country, Central. So California's in Pacific time, so it's 3 hours behind. It's 8:10, and the minutes don't change. It's just hours. And as a matter of fact, it's 11:10 a.m. in New York. What time is it in Hawaii? It's 5:10. They're 6 hours behind. That's really good. Hawaii's super far away. So let's talk more about the details of this here and how this works. So please pause and copy this down. And where we get the 15 degrees per hour is we rotate once, it's 360 degrees all the way around. It takes us 24 hours. You do that math, we get 15 degrees per hour. Therefore, each time zone is about 15 degrees longitude wide, but not totally, perfectly to the longitude lines. Because we have to make it work. We have to make it work for the state boundaries and country boundaries. You don't want a time zone line going right through Main Street of your town. So on one side of the street it's 9 a.m. and the other side is 10 a.m. You can't have that. So they kind of fudge it, as you'll see in this picture here, right? So here are the lines here. Don't go by the lines, go by the gray areas. The gray and white denote time zones. Use these, right? So this is the Eastern time. That's where we are in New York. All this the East Coast here. Central time, Mountain time, Pacific time, and then it goes off here. It gets a little weird with Alaska and Hawaii because they kind of just mess with it to make it work because they're so big and there's not a lot of people live, especially in Alaska. And Earth rotates in this direction. If you guys just remember that, it rotates sort of counterclockwise if you're looking at it from above, counterclockwise. And that's why we are ahead of the West Coast, and that's what I usually remember. The sports thing's really got cemented in my mind for me from when I was a kid. So for instance, I drew in if it was nighttime. So right here, I tried to draw this. For us, it's sunrise. We are rotated into the light part of Earth, like on the previous diagram on the previous page. We're experiencing sunrise, but the rest of the country, it's still dark for them. So they're behind. They will experience sunrise when they rotate there hours later oftentimes. So that's why I put that in there. Right? So what I have here is Earth rotates counterclockwise when looking down at the North Pole. Please copy that. And then this question is, what is the time difference between A and B? So let's go back to, do I have maybe here? A and B, time difference, like how many hours, right? So A is here and B is here. So I just count it like this. A, we're going one time zone away. We're going back, but it's 1 hour, 2 hours. It's 2 hour change. So Mountain time, like it's just out in Colorado, for instance. Colorado is in mountain time, so it's 2 hours behind. Crazy when you get into booking a flight, never booking a plane flight. You see what time you get there, like the times look weird. Like I thought it took a long flight, but then they're also 2 hours behind. So that flight oftentimes will take 2 hours longer than is say on the ticket. So therefore, that answer is 2 hours. What's the difference between the time difference between B and C? B is here, C is here. So this is each time zone is an hour. So it's 1 hour time differences from the mountain time to the Pacific time. Pacific time, C is 1 hour behind B, but it didn't ask that. It just wants to know the hour. So it's 1 hour. If it's 3 p.m. at A, what time is it at E? A and E. 3 p.m. at A, I think I wrote it in. If A is 3 p.m., what time is it? What did I say? E? E is here. So 3 p.m., 2 p.m., 1 p.m. Oh man. Sorry to do this again. 3 p.m. and then 1 hour. 2 p.m., 1 p.m., noon, and this is the next one over. So that's 11 a.m. E is 11 a.m. 11 a.m. Hopefully that makes sense. If you want to try the next one, you should try it. Now I'm going to do it. If it's 5 a.m. at C, what time is it at B? 5 a.m. at C, what time is it at B? Right, so it's one time zone over, but I'm going this way. So am I going up or down? Time-wise, I'm going up. So 5 a.m., 6 a.m., B would be 6 a.m. Okay, I'm gonna leave this last. Hopefully you pick this up. I'm gonna let you finish these last two on your own. Do your best. Do your best. But it was a pleasure learning with you today. Thanks for watching. I'm Mr. G.